Okay, hi everybody. So this is the very, very short screencast here so I can give you this formula right here. When you're given a polar function, r is a function of theta, is there a way to get to dy dx? And the answer is yes. I'm going to show you, I'm going to give you what this is here, and then I'll show you the derivation, okay? So when you go to dy dx, okay, dy dx, here's what I want you to put there in that space, okay? Dy dx, okay, so, and again, dy dx is the slope of the line tangent. Okay, dy dx for a polar function is going to be this expression right here, dr d theta sine theta plus r cos theta, all over dr d theta cos theta minus r sine theta. It is definitely in your best interest just to memorize this. This is dy dx. Let me, though, show you the derivation here. And again, you don't have to copy the derivation down. I think there's something very satisfying about knowing why and how the math works. So let me just turn myself around here, okay? So let's start with the original premise, okay? So this original premise is if you're given a function of theta, how do you get to dy dx? Well, here's the proof. You know that in polar functions, y equals r sine theta and x equals r cos theta are two of the conversion formulas that we learned on the very first day of polar. So take a look at this equation right here. If y equals f of theta sine theta, and look what I did, I just replaced r, which is a function of theta. I wrote r as f of theta sine theta. The reason why I did this is because now I can take the derivative and say, well, this is dy d theta, right? Because the independent variable here is theta. Here, there are two independent variables. I wanted to get to one independent variable. When I take dy d theta, I have to use the product rule. And all I did now was replaced f prime of theta with dr d theta and f of theta with r. So this is dy d theta. In a similar vein, if x equals r cos theta, I replace the r with f of theta because r is just some function of theta. Here is dx d theta, and then here is dx d theta back in terms of r. And if you are given, right, or if you've found dy d theta and dx d theta, the way to get to dy dx is dividing the two. So this feels probably similar to parametrics, okay? And here is your dy dx. So we'll do a very simple example, and you may, need this for your homework tonight. But, you may have a situation like this. Let's say you have r equals 2 plus 2 cos theta, and the question here is asking you for the slope of the line tangent to this curve at a point when theta equals pi over 4, okay? Well, we're going to have to take take r as a function of theta and calculate. Let's see. Dy dx is going to equal dr d theta, which is negative 2 sine theta, okay, times sine theta. I'm just going to write this like this, sine squared theta, plus 2 plus 2 cos theta times cos theta, all over dr d theta, once again, is negative 2 sine theta. Now there's the cos theta, okay, minus 2 plus 2 cos theta times sine theta. So here, all I've done is I've just, found now dy dx using this formula. I found dy dx in terms of theta. And then if I'm asked to evaluate dy dx at a particular value of theta, it's just a matter now of going, okay, dy dx at theta equals pi over 4 is going to equal, okay, and this part you can probably do with your eyes closed. Because we know that once we get to a numerical answer, we can stop. And here, everyone, we have the slope of the line tangent to this cardioid at theta equals pi over 4. I'm going to make a note to myself that I can kind of eyeball this and see if it's going to be a negative number. Okay, it's a negative number, so I fully expect the slope of the line tangent to this cardioid to be negative at theta equals pi over 4. Okay, and now you are well set to do the homework.